beginning something, Devjit?
Yeah. So,
Okay, please start. Please start.
Professor David Airey, I will welcome you in this session webinar, Terzaghi Day extended part of the Terzaghi Day celebration. So, I thank you on behalf of IGS Silchar Chapter to accept our invitation, and hope everyone will enjoy. So many students are there. So, so Hon'y, you can start. Thank
Yes,
you.
sir. Hello, everyone. I am Hon'y, and on behalf of IGS Silchar Chapter, I welcome you all to the second session of our Terzaghi Day celebration. Today, we have Professor David Airey with us. He graduated from University of Cambridge in the year 1979 with a BA in Engineering and Masters and PhD in Soil Mechanics. He took up a position as Research Fellow at the University of Western Australia in 1987 and moved to the University of Sydney in 1989. Professor Airey was acting head of School of Civil Engineering in the year 2016. His research interests include all aspects of experimental geomechanics, from fundamental soil tests to laboratory model tests and field testing. His current research projects include ground improvement, such as rolling dynamic compaction, proof rolling, polymer modification, soil foundation enhancement, unsaturated soil dynamics and liquefaction, fundamental soil mechanics, and mechanical effects of CO2 geosequestration. He is the editor of Geotechnical Letters and on the editorial board of several journals. Hoping you will all have an amazing learning experience with sir. Over to you, sir.
Okay, so can you see my screen?
No, sir, it is not visible.
Yeah, that's what I thought. So how do we get to see my screen? Is there a button I have to push? Present now? I do that?
Yes, sir. Yes, sir. Yes, sir. Present now.
Okay. A Chrome tab. No, okay, I've done the wrong thing. Wait a minute.
You can first open the presentation.
You know,
open
I've done
the PPT
that.
file.
Yeah, done
yeah,
that.
then
Go to a window or your entire screen.
Your entire screen. You can share your entire screen and then go to the presentation part. Presentation file, then you can open then.
It's not letting me. Wait a minute. Let's try that.
Oh, yes, sir. You can now open your presentation. Yeah, it's visible now. Yeah, it's visible.
Excellent. Okay. Yeah, we're all using Zoom here, so it's yeah, this is different. Okay, so yeah, welcome everyone. Okay, so I'm going to be talking about some work we've been doing over several years in looking at rolling dynamic compaction. So basically, I'm assuming you don't know much about it. It's really something that's taken off in Australia, and it's sort of getting to other parts of the world slowly. So I'm going to try to explain what it is, and then why we're doing research into rolling dynamic compaction. So yeah, we'll cover a bit of the background, previous work, of which there isn't much, as you'll see. And mostly what we've been doing is laboratory studies. So that's mostly what I'm talking about. My colleagues have been involved in some field studies, and I'll mention them briefly. And then we're trying to do numerical analysis. So I'll just mention that and some of the challenges that is involved with that. Okay, so I just want to mention that I'm not just presenting my own work here. I've been doing this in collaboration with a big team at the University of Adelaide, where Professor Mark Jackser is the leader. And yeah, there's the first about 5 people on that list have all got PhDs basically on this project. and are still going. So there's a large number of people involved. I'm also mentioning here from the University of Sydney, Professor Day was also here at the start of what we were doing at Sydney. So it was a long time ago. He was a visitor, but he'll recognise one or two of the pictures because he worked on it. So it's a big project. We've had support from the Australian government and also from Bruns, who are one of the main suppliers, at least in Australia, of the rolling dynamic compaction equipment. Okay, so what is it? Okay, so basically it's a compaction technique, and it involves towing these things along behind a tractor. So normally when you're doing compaction, you have a circular roller, but you'll notice that these are all funny shapes. So here we've got a sort of triangle, this one is square, and this one is pentagonal. And the idea is that as they rotate, there's an impact as it goes around, an impact on the surface, and that then leads to improved compaction. So one of the benefits of this is that because it's being towed, it can go relatively quickly. So typically 10 kilometers per hour, which is 3 to 4 times quicker than a normal roller. So that's an advantage. And the other big advantage is the depth. A normal roller you can compact to maybe a half a meter at most, but typically 300 millimeters, whereas these devices in the right soil have been reported to compact down to up to 7 meters. So it's significantly more energy being imparted into the ground. Okay, so why the need for research? Because these things have been around for a while. So the problem is a practical one. If you're an engineer on a site and you have to consider what type of compaction equipment to use, then you're normally going to be suspicious of the construction company trying to get you to use their particular device. And this is essentially what happens with rolling dynamic compaction. It's promoted by mainly Landpack, but there are some other companies who will tell you that it will work on your site almost irrespective. But how well it will work and so on is never really clear. You're relying on experience with similar sites so that they can be confident it will work. So we have an absence of any sort of theoretical approach or any analytical method. So the consequence is that, okay, because generally this is being used on fairly big construction sites. It wouldn't be used on a little residential plot. But still the cost of running a field trial is large. Because you've got to do the trial, you need equipment to come to the site, there's instrumentation required, and then you've got to assess whether it's achieved the objectives. So this is costly, and because this is seen as almost step one in this process, it means that currently rolling dynamic compaction is not used anywhere near as much as it could be. There's also practical issues with specification. So particularly in Australia now, it's obviously different in different parts of the world, but the way the construction work is specified, what you have to prove at the end of the day. So whether it's just that you run the machine up and down the site a certain number of times, or whether you have to demonstrate that you've actually achieved something, makes a big difference to the sort of the whole procedure. Then, as I mentioned at the start, there's one of the difficulties that engineers have in using this approach is that it relies on experience of the equipment suppliers, the Landpacks and Bruns and other companies, when they tell you that it will work on your particular site. Okay, so the effects of the soil type, the state of the moisture are really not very well defined. They're not clear at all. In many cases, a working platform is needed on the surface, otherwise the device will sink into the ground. So that's another sort of uncertainty that you need to sort of consider. Then there's issues with noise and vibrations because it's an impact device. Then as it hits the ground, the vibrations travel through the ground and can damage nearby structures and also underground pipes and so on. So there's you know, that's works against using an impact type of device such as the rolling compactor. Okay, so I've mentioned engineers are skeptical about the claims from the companies that are promoting it, and then there's limited actual sort of evidence that it works. Okay, the companies obviously promoting it have some evidence, but it's not in any clear and well reported sense. It's not well reported in the you know, the academic literature. So you know, this is clearly a limitation. Okay, so that's sort of where we started. We were basically approached by Brooms, who's you know, I'll say a bit more about that in a minute. And what we set off to do was to do laboratory and field studies to try to get some more data to see if we could understand a bit better what was going on. And then there's some numerical analysis which was done as well to try to you know, go from the specific to the more general situation. Okay, so just a bit of background on compaction. So I wasn't sure if you know, what do you know? So, but I'm assuming everyone knows what compaction is. Okay, it's like the most common ground improvement technique, widely used because it's very cheap. The equipment is widely available, and the equipment is it comes in all shapes and sizes. One of the things that happens with normal compaction is that you are preparing the soil for compaction. So on a typical road pavement type project, or even on a small plot, you would be preparing the soil, controlling the moisture content, doing some tests of the soil type, and you would be putting it down in small layers, thin layers, and then compacting it. Again, and depending on the energy and the size of the site, you can use bigger or smaller machines. So that's the sort of normal process, but it is limited because you have to use these thin layers. So the normal technique for a big sort of construction site is a vibratory drum roller, and I'll come to how they work in a second. So the problem is if you have deep in situ soils which are weak for some reason, you don't really want to have to dig all the ground up and to relay it in layers. That's really very costly, and some other sort of ground improvement then is required. And this is really where the impact compaction type of machinery comes into its own. But we're going to talk a little bit about vibratory rollers, drum rollers to start with. Okay, so here's a picture of a so it's a bit out of focus, of a vibratory drum roller. Okay, so I'm sure these are common in India too. Okay, this is like the standard machine for compacting soil for roads, railways, and that sort of thing. So what may not be so clear is that they have a little eccentric mass inside the roller, which accentuates the compaction effect. Okay, so it's obviously a heavy machine. These machines typically weigh, 10 tons or something of that order. But they have a little mass in here which goes round at quite a high angular velocity and creates some extra force on the ground. Okay, so if we just want to think about what's that vibration doing, okay, and this is sort of just getting us onto the rolling dynamic stuff in a minute. So to understand how it's going to interact with the ground, we have to idealize the ground. So we have a spring and a damper, and then we can treat this whole system as a single degree of freedom system. So you may have done something like this in your mechanics study. Okay, and then we get a picture like this of the amplification against the frequency ratio. So the thing to see is that you have issues with resonance with these devices. So you have to sort of not operate in this region here. You actually want to operate up here, where you're getting the maximum benefit from the rotating little mass here. Okay, but of course, all these properties, the stiffness of the ground, the damping, depend on all sorts of things to do with the soil and the machine and so on. Now, one of the problems is, of course, and hopefully you can appreciate this, if we keep going faster and faster, the mass at one point in its cycle is going down and we have extra force acting on the ground, but at some other point it points up, and then if we go fast enough, it will actually lift the drum off the surface of the ground. So this is actually what happens. Okay, so here's a picture from Adam, who's done a lot of work on, so he's from Austria, a lot of work on these roller compactors. And the interest here is in controlling this by some fancy algorithm on the drum, by controlling the speed of the rotating mass to optimize the performance. So if we just concentrate on what happens in the middle here, this is the interesting bit. Okay, so if the mass is going around slowly, then the drum is in continuous contact with the ground, and we get some sort of contact force like that. As the rotating mass goes faster, you get a bigger force on the ground, but also it starts to lift off. That's the sort of little gaps in here. And if you keep going, then it starts to jump. And in principle, this is the optimum place to be to get the biggest effect, compaction effect, from your vibratory roller. But it's not so easy to actually control it to be in this point. If you go too fast, then the roller starts jumping around. Okay, so it rocks from side to side, and you get very uneven forces occurring, and then finally it becomes chaotic. So this bit at the bottom here is no good. So this is the challenge. There's only so much you can do with this eccentric mass to increase the force on the ground. Okay, so if we want to go beyond that, we then come to some sort of dynamic effect. So I've just mentioned sort of conventional dynamic compaction, and then we'll sort of focus in on the rolling dynamic. So this is conventional dynamic compaction, where we have a big weight, it's dropped onto the surface of the ground. Okay, so previously we were talking about with the vibratory rollers, we could compact maybe 0.3 of a meter to half a meter at most. With these big weights, we can now compact depths of up to 20 meters. So 10 meters is sort of typical, but with enough weight, you can get effects of compaction all the way down to 20 meters. So it's a very cost-effective technique, but we're going to have issues with vibrations. Okay, so the vibrations are going to be created in the ground, and they're going to travel through the ground, which means you can't really do this anywhere near any built-up sort of areas or where there's any services that are in the ground. So this is the big limitation of this technique. In terms of you know, how does it work? Well, no one really knows. Okay, that is the answer. But there's been quite a lot of field studies, and there's this magic equation down here which says the depth of improvement is the square root of the weight times the height you drop it times some magic number n. And n varies depending on soil type and the position of the water table. And you know, these are the sorts of numbers you're looking at, between 0.3 and about 0.8. So there's a big table here, but you'll see most of the numbers are in that sort of range, 0.3 to 0.8. So we started off looking at dynamic compaction, see if we could understand a little bit better what was going on with it. And just to show you what it actually looks like in practice. Okay, so it's pretty simple technique. Doesn't take very long. So the way it works is that each position like this, we would drop the weight maybe 15 times, and then you move on in a sort of a grid pattern around the site. So we had an opportunity to be involved in a case study near Sydney. This is actually from that case study. It's in the west of Sydney. So the weight there was 16 tons. They were dropping at 23 meters and 16 drops in each location. Oh, so we move on. Okay, so this is a little picture here showing you the pattern. So that you go across the site. So doing the red ones and then the blue ones and then the white ones filling in the gaps. And this is what you see on the surface. So you end up with all these holes. And sometimes, you know, and what you're trying to achieve is compaction, okay, so that you're expecting the ground to settle. But the observation was that a lot of the time, the ground surface actually heaves up. So this is obviously not a desirable outcome. So at this site in Western Sydney, the student who was working on this just compared how much of a hole you created versus how much the soil was heaved up on the side, and plotted that across the site. So this is what you can see here. So where it's green, the soil is heaving up more than the compactor is going in. So in this region here, dynamic compaction really was doing nothing. Where it's purple, then it was looking like this, and the ground was being significantly compacted beneath the site. Okay, so you know, we are facing one of the big problems with geotechnical engineering generally, is that we're at the surface and we really don't have much clue what's happening at depth. So there is surprisingly little data on dynamic compaction, even though it's widely used, about exactly how well it works. So one of the things we did at this site was to put in some extensometers to measure the settlements of the ground. Okay, so this is if I just go back. Yeah, so here you can see this is where the extensometer was positioned, okay, and going down to rock, which was 20 meters down. So what you see is that near the surface, you get the soil heaving, okay? So we don't have compaction at all. We have, in fact, the reverse of compaction. The soil is actually loosening up near the surface. But then once we get down a bit, so down here in this case to 4 meters, then we have a fairly significant effect down, and here was rock at 14 meters. So a significant compaction can be achieved, but at this, you know, we have this problem near the surface where the soil isn't getting compacted. Another thing that was done at that site, I mentioned the issue with vibration, and that site in Western Sydney was a very large gravel extraction site that had been used for 30 or 40 years, and they were trying to make it suitable for residential construction. So it had a quite deep deposit of fill, of uncontrolled fill, and there was no buildings or no infrastructure anywhere nearby. So vibrations weren't really an issue there. But this is the sort of data that you get, and there's a curve here from Maine in the US who'd looked into this problem before, and basically the results agreed with the published data. So if you just look at this table at the bottom here, you know, really you need to be having, so we're plotting peak particle velocity against distance from where you're dropping your weight. We really need to be having peak particle velocities of 5 or less to avoid any sorts of damage. Again, and also, of course, there's damage of things that are buried in the ground as well. So if you just look at this, and when we go to 5 and come across here, you'll see that you have to be 70 or 80 meters away from this weight dropping on the ground to avoid damage. Okay, so this is an issue with impact compaction, and it's an issue with the rolling dynamic compaction. So I'll come back to that later. But just remember this chart. We need to have peak particle velocity down below about 5. So that controls how close we can operate to existing infrastructure. Okay, so we've talked about rollers, conventional vibratory rollers, talked about dynamic compaction. I'm going to be talking the rest of this presentation about the rolling dynamic compactor, which you'll see here is also called high energy impact compaction. There's a couple of other techniques that are sort of in this group. There's a thing called a rapid impact compactor. So what happens here is there's a big lump of steel which sits on the ground, and then there's a jack here that applies a cyclic load. So you get the compaction from this cyclic load, and then this machine sort of is relatively mobile and moves around the site. Okay, so it's obviously not as quick as the tractor, but it can cover a fair area quite quickly, and it's similar in terms of the depth that it can compact the soil. And then at the other end we've got vibroflotation. Okay, so that's a rather specialized technique where you're filling up the hole with stones and things to further increase the compaction. So we're not going to talk about this one. We're just going to talk about here. Okay, so a bit of the background. Rolling dynamic compaction has actually been around for quite a long time. It was first developed in the late 1940s in South Africa, where they have a lot of trouble with collapsing soils. I'm not sure exactly what the cause is, but they have a number of issues there with collapsing ground. Anyway, so this was for a pavement type application, and the idea was that they could use this heavy sort of hammer, put it along on a tractor, and it took some time before the work got noticed by anyone else, because from the late 1940s, it wasn't until 1971 that the first paper was published. So quite a bit of development obviously happened in that time. And then there was a master's student, maybe it was even a PhD thesis by Clifford, where really people started to take notice. Now, still not much happened, okay, but what did come from this is that the device which had been developed in South Africa was, the patent, I think, was purchased by Bruns in Australia, and they set about trying to, so Bruns produced rollers for a whole load of equipment for compaction and pavement construction. So they saw this was just an extension of what they did, and they invested in some of these roller compactors. And then eventually Landpack, who are probably now the biggest company doing this, have developed their own device. Okay, so really, although it started in the late 1940s, it wasn't until 1990s that this technique really started to get used in much of a way. Okay, so now the literature review here is short because really there isn't much to talk about. So what has happened since that time? So since the 1990s is that a number of field cases have been looked at, and basically it's a before and after study with either a cone penetrometer or a dynamic cone penetrometer, that shows that compaction did indeed occur and to what sort of depth that it occurred. And so there are quite a few papers of that type, but none really tell you, how to do it, how well it works in different soil types, exactly how much depth of improvement you can expect. It's all very unclear. So Bruns basically sponsored a whole lot of studies. So they were one of the main people pushing this. And they started actually, documenting. So we had a range of papers coming out of Bruns. So there's one in Sydney where the water table is right near the surface, and it just compacted about 1 meter, which is not all that useful. But in other places, same equipment, also in sand in the Middle East, they were getting compaction down to 7 meters. So there's a wide range of numbers there, and a wide range also in the effectiveness of the compaction. More recently, it's been taken up in China, and in China they've got a lot of clay material on the east coast of China, and so they've been using it for clays, whereas in Australia it's been used pretty much exclusively for granular materials and granular and waste materials. So old landfills, things like that have been used. It's also been used for controlling permeability on levees and things like that. So there's a range of applications. And another one was the mine sites in Australia. They had a trouble with the tires on the big mine machine were getting damaged by the road surface, and it was found that the rolling compaction, because it basically crushed the material quite effectively, it ended up saving them lots of money on tires. So there's a sort of a range of applications. Okay, so just before we get into the what we've actually done, so just taking a minute to think about what is the aim of compaction. So, as it's taught in most soil mechanics courses, the whole idea is to get to the maximum dry density, and to do that you need to have the soil with a particular moisture content, the optimum moisture content. And that's seen as sort of a target, and if we get most soils to that sort of state, where we do a standard compaction test, then we expect to get reasonable performance. Now, there's a lot of interest nowadays in stiffness rather than density. So one of the problems with compaction is that density is quite hard to measure. So people have moved on to measuring stiffness rather than density. And of course, stiffness is one of the key benefits of densifying the soil. And ultimately we're trying to reduce the surface settlement. So we just need to remember that these are the things we're actually trying to achieve. It's not just about compaction as such. Also, reducing the permeability is often quite important in construction. Okay, and then we have some methods for assessing how well this works, right? So there's a range of things that people have used, and you can find these in the literature. So the most common are the first two, to do a cone penetration test before and after, so you can demonstrate that something's happened. And similarly with a dynamic cone penetrometer. I don't know if that's popular in India, but it's very popular in Australia. Everyone hates this device. If you're a young geotechnical engineer, yeah, this is a sad thing that we really need to get rid of. You have to lug around a 7-kilo weight and drop it into the ground. It's hard work and dangerous. So there are some more modern things. So we can try and use geophysics, plate load tests, which help with measuring the stiffness. And then there's attempts at the moment to try to make use of the information from the compaction machine itself to get some indication of how effective the compaction has been. So people talk about compaction meter values. So this can work in a variety of ways. So for instance, it can just be the energy from the tractor, just keeping track of how much work the tractor is doing, or it can be accelerometers which are on the axle, and then from the accelerations you can work out how much you can get some idea of the stiffness of the ground from the way the weight bounces around. So there's all these techniques that are out there, but the thing to see is that none of them actually measure density, okay, which is number one, what we're trying to do, at least not directly. CPT certainly doesn't, dynamic cone penetration doesn't. Geophysics, in principle, can measure density. We're measuring the velocity, but the shear wave velocity depends on the stress as well as the density. So it's hard to pick density. Plate load tests, okay, they also indirect, and then compaction meter value, definitely very indirect measurement. Okay, so what has been done? So I'm not going to explain everything that's been done. As you saw, there was a very large number of people that have been involved in this project. I am just going to show you some results of a current PhD student at the University of Sydney. This is what he's doing. And then we're going to look at some field tests that were done at the University of Adelaide. So this is our setup. So what we have is a model scale here. This is a 1 in 10, roughly, anyway, 1 to 10 scale of the device you saw before, which we are pulling around. We have a motor here which drives this wheel, and the wheel basically tows this along behind it. So one of the things that's important is that it only rotates by friction. So this wheel is not being driven at all. It's just on this axle here, and it relies on friction with the sand to make it rotate. Okay, so this is something that's important, as we'll see when we look at the results. Okay, and this is our tank where we fill up with soil, and we're taking various measurements of the soil in there. We've also done some tests with a 1/20th scale. Okay, so we've got 2 different sizes that we've been looking at. This is what they've been doing at the University of Adelaide. The device that we've been using at the University of Sydney is sort of copied off the Landpack device, which is a 3-sided roller. But at Adelaide, they've made a copy of the Bruns 4-sided roller. Okay, so this is essentially a almost perfect copy of the Bruns roller, including this spring-driven mechanism here, which is at least claimed by the manufacturers to improve the performance and increase the impact on the ground. Okay, so the principle of the thing is similar. They have a tank of sand. This device gets towed. They've just got a wire that connects to this device here, and they just tow it along across the surface of the sand. And then there's a whole lot of instrumentation in the sand here to measure what's going on. I just mentioned also there's another person doing this in China at the University of Shaoxing. So the apparatus looks very similar, right? There's a big tank of sand, and in this device, there's a wheel that starts here and it just goes to the end, then it lifts off, goes back. So it's not on the circular track like the ones we have in Australia, but the idea is pretty much the same. So I'm going to be talking about some results from this later on. Okay, so we've made a number of measurements. We've looked at the surface settlement. We have buried settlement plates. We've measured the soil movements on the front face. So I'll explain more about that later. So you might have noticed there was a perspex window on the front of the apparatus. So we are actually looking at the sand movements behind that perspex face. At Adelaide in particular, and in the field tests, there's been a lot of work on the stress distribution. Burying pressure cells, so earth pressure cells, so miniature ones that are buried in the ground, and then used to get the stress with depth. And also there's been some tactile sensors used as well to get more than just a point measurement, to get it over an area. And then there's also been accelerometers, which have been often connected to the pressure cells so that you can get not only the force, but also the movements at the points of interest. There's also been some nuclear density probes used. So in line with current practice this is the sort of the gold standard of estimating how effective your compaction has been. And we've been measuring penetration resistance as well. So I'm going to show you some results now to get a sense of what actually happens. So this is the pictures of the surface. Okay, so what we have here is the sand surface. We're taking photographs of it. So we have a special light scanner. It's not actually the camera as such, but it uses a special light that has some sort of texture in it that it then picks up the distortion of that light, and then you can get very accurate measurements of the surface. So this is just looking along the direction of the track, and you can see that we have this very wavy surface here. So this is because of the way the thing works, right? It hits the ground, there's an impact, and then you're towing the axle along, and then the friction between the compactor and the sand then causes it to roll. Okay, and we'll see some more evidence of that. So basically where you get the troughs, this is where it impacts, and then it rolls around, and then it hits again here, and it rolls and it hits. And then if you look at the red line, so this is the surface after the first pass, and then the blue line after the 20th pass. And you'll notice that the troughs are in different places. So it's actually pushing the sand around as well as it's compacting it. Okay, and we'll see more evidence of that in later. Okay, there's also some practical issues when you do these tests, that our compactor can't hit the surface. You have to lift it off the surface. It has to lower into the tank, and then you have to lift it off at the other end. So there's only a limited region where we can reasonably say it's kind of a uniform compaction. Okay, so that was that previous picture. Let's just go back for a second. This is along the direction of the tank. Okay, so our tank was actually, it's about 1.5 meters. So this is the wheel rolling in this direction. Okay, so now we're going to take pictures sort of looking into the page here, if you will. Okay, so this is the cross section. So this is where the compactor wheel is running, and this is the other half of the tank behind it. And what you can see is it's pushing the soil up. So initially it goes down, but then as you keep going, the compactor is actually pushing the sand up, and we're getting this heave of the sand beside the track. Okay, so just as we saw with the dynamic compaction in that field study with those big mounds of soil, we get the same sort of thing happening here. So this is a loose sand, so mostly it's compacting, and the heave is not that significant. But if you do this with dense sand, so what happens is that the heave bit here is almost as significant as the compaction you get here. So you're mostly just loosening the sand in this region. So it doesn't work so well with dense sand. Okay, so that's what happens at the surface. But there's an issue with the surface is whether that's actually telling you anything useful. Okay, and the reason for that is that the compactor is actually pushing the sand in front of it as well as pushing it off to the side. So we've got some little sensors here, little buried plates, where we're able to measure the movement of the ground that's beneath the surface. So this is what you're seeing here. Okay, so we can see the settlements building up over time, and it looks, like it happens in a fairly steady way. But just notice that we've got these discrete points, and each time the compactor runs along here, it hits in a different place, and it almost certainly doesn't hit directly over these plates. So what we can see is that we are indeed compacting the soil at depth reasonably well, even though at the surface something funny may be going on. Okay, so some penetration tests. So this is the loose sand. So this is our initial penetration, and this is after 20 passes. So you can see that the penetration resistance has increased significantly, and this is for initially dense, medium dense sand, relative density of 0.6. So this is the initial curve here, and this is after 20 passes. So you can see here we're having a big effect. Here with a medium dense sand, not very much, but we're still getting a bit of densification at depth, but really nothing near the surface. Okay, so if we just look at trying to make sense of this, we can try to estimate the increase in the relative density. So this is the sort of equation that people use, relating relative density to the penetration resistance. Depends on the stress, and we've got 3 fitting parameters here. So the trouble with this is that although we can do this for our laboratory tests, this isn't all that useful in the field, because we don't know what the appropriate fitting parameters are. Relative density is not easy to determine from cone penetration tests. And these squares are the results from our buried plates. So you can see, although we're predicting some sort of increase, it's not at all consistent with what we're getting from the cone resistance. Okay, so there's a number of issues. Of course, we're assuming here that we've just got purely vertical movement, and we've seen that the soil is not moving purely vertically. So the plates, we think, are less reliable, but it does sort of show some of the challenges with trying to understand exactly how much densification you're getting. Okay, so that's one of the big issues is, we can show we're getting densification, but how much? And can you predict how much? Okay, so I just want to say a little bit about the photography. This is just for Professor Day, because this is what he did when he came visit us in Sydney. So we've carried on doing this. So we have a high-speed camera here. So we're taking 1,000 frames per second as our wheel rolls across the top here. And then we've just got the sand here behind a perspex window, and we're looking at the movements of individual sand particles. Okay, so lighting is obviously important so that you can actually distinguish the sand particles in your picture. And then we're using something called digital image correlation. So you're probably not familiar with this technique, but basically you look at 2 pictures and then you get a pattern. And what you do is you shift the one picture relative to the other to find where you get the best match. So this is a correlation between the 2 pictures, and what you're hoping to see is a nice peak like this, which is where you have a very good match, and then you can determine how much you had to move picture 1 relative to picture 2, and hence you can get the displacement. So that's the idea behind it. Okay, so this is I've just got a couple of slides of pictures of this. So this is what you see as the wheel is rolling around. Okay, so it's an impact compactor. So this is the impact happening here. And you can see at the impact, it forces the soil down and also off to the sides, right? And this would actually, would come up as well a bit, but we've obscured the top, so we can't see that. And then as the thing keeps going, so the wheel is rolling. Okay, so this is going around this way. So this, when we come to this picture, right, what was here is now here. And what you can see is it's now pushing the sand in front of it. Okay, so we're pulling on the axle here. The thing is rotating just due to the friction, and we have a frictional force which has got a component horizontally. So the sand gets pushed in front of it. There's really no compaction happening at this point. Then we come to here. Okay, so now we've just gone around a bit further, and at this point the axle is at its highest point, and you can see there's almost nothing happening in the soil. Okay, so we've got there's some, you know, due to the rotation, there's a upwards force here, which is, you know, acting against the weight. So no movement in the soil at all. And then we keep going. So we're going to get the next impact when this bit here hits the surface. So this is just before the impact, but it's rotating about this point here. And now the frictional forces are pushing the soil out behind it. Okay, so there's a little bit of forwards motion, but mostly the soil is getting pushed backwards. Not much happening down here at all. Okay, so this is the process that is going on. Okay, there's some details there about the pictures, but we don't really need to worry too much about that. Okay, so this is just to show you what happens if we just keep going. The idea is we look at a whole cycle. So this is from one impact to the next. Then you start to see, you know, despite the soil moving backwards and forwards, you do see a significant region down here where the soil is being pushed downwards. This is in the first pass. This is the same picture in the 10th pass. And what you can see is that there's almost nothing happening at the surface here, because the soil is, by this stage, mostly going backwards and forwards, but there's still a bit of compaction happening. If you know, you might not see that very clearly, but there's still all the vectors down the bottom here are going downwards. So you continue to get some compaction, but there's not much more compaction happening near the surface. The soil is just going from side to side, and indeed also being pushed forwards by the device itself. Okay, this one's just for Professor Day. This is when he visited us in Sydney. This is what we were trying to do. So this is a straight dynamic compaction with a load coming down vertically on the soil surface. So the thing to see is that what you get is a standard bearing capacity failure near the surface. Okay, so if you've done a bit of soil mechanics, you'll be familiar with that idea. And then there's this region at depth where the soil is being pushed vertically downwards. Okay, and this is what we're seeing, right? We're seeing the soil near the surface being pushed sideways and upwards, actually getting looser. And then we've got this region down here getting denser. Okay, so I'm conscious of time. So just briefly, field tests. So tests have been done with this four-sided roller. There's been sensors buried in the ground at different depths. And from that, you can estimate the pressures. Okay, so 1 MPa. And from the accelerometer, you can get the displacement that's happening. And then you can get load displacement responses of the ground. Okay, so you can see that the settlement's gradually building up as the device is passing over it. And if you put the sensors at different depths, then you see how the stress decays with depth. And we see in the laboratory the same sort of decay. It drops off fairly rapidly as you go down. This is showing the position of the pressure that you measure on your pressure cell, depending on where you are relative to the impact and with different velocities. Okay, so the important bit about this is that if you take these curves down the bottom, this is when we're going 8 kilometers per hour. So this is the sort of slowest speed that these devices run at. But the sort of target number is around 10 to 12 kilometers per hour. And that gives you this curve up here. So you can see you've got a peak pressure of about 1 MPa, and it drops off a bit as you go away from that. Okay, so we're looking at 800 millimeters to either side here. But if you go faster, so we're now just going 13 kilometers per hour, we lose that peak altogether. We've now got this upturned result. So what actually happens is that just as you had with the vibratory roller, things get out of control. And it's not doing what it's meant to do. It's sort of bouncing along the surface and it's rocking from side to side. So not only is it very uncomfortable for the tractor driver, but also you cease to get the required compaction. So there is a limit to the speed. Okay, so this is an important aspect of this. The amount of energy you can put in is limited. I mean, and hopefully you should appreciate, of course, that the faster you go, the more energy you're putting into the ground, which is why the stress here is going up as the speed goes up. But we see there's a limit, okay, and the operators are well aware of this limit because the thing starts getting out of control beyond that. Okay, vibration. Yeah, so remember our 5 millimeters per second number, so that's around here. So you need to be about 30 to 40 meters away, or you have to be that distance away from, or maybe 20 meters from other buildings and so on to use this equipment. So it's not suitable for residential sites. Okay, it needs to be out in relatively open and large sites to be able to use this, because otherwise you're going to have this issue with vibration damaging buildings and damaging buried infrastructure. Okay, people have been trying to do numerical analysis. So numerical analysis predicts stresses, it predicts strains, and I'll just show you this little picture. And you can make this sort of thing happen. Okay, so one of the problems we have is that when we're doing this, we're actually forcing the thing to roll here. So it always hits at exactly the same point each time. So we're not actually able to very well model the friction between the compactor and the ground, which is actually important. It both limits the amount of energy that goes to the ground and it controls the motion. So although we can get some predictions, they're not necessarily all that good. So the stresses and their distribution with depth agree pretty well with between experiments and model tests. Okay, so the numerical analysis gives rather more stress at the surface and rather less at depth compared to the experiment, but it's capturing fairly well what's going on. But if you look at the settlements, yeah, we're not capturing this initial large settlement, which is because a lot of the sand just gets pushed out of the way. So, you know, so that's obviously, you know, quite tricky to model. Okay, so I'm just conscious of time. My hour is almost up. So just where we started, right? There were, I mentioned all these challenges at the start, so I won't go through them all again, but just try to summarize by what has been achieved. So there's been a lot of work done, okay, both field studies with instrumentation and laboratory studies where we've tried to clearly identify the mechanism. So we have a much better idea now about how rolling dynamic compaction actually works. And what's clear is that the actual impact is the all-important bit. The rest of it is just rolling around. Okay, so that's the one of the key things. The importance of towing speed. Okay, so this is an issue in terms of specifying how people go about doing this. So it's certainly shown the importance of having some control over the speed, and it depends on the soil type and other things as well. So that's clearly come out of all the research tests. The scale, the lab tests and the field tests, basically they're all giving the same sort of results in terms of the depth of improvement and the stresses. And a predictive AI tool has been developed. So using cone penetration data and some other information, we're able to make some sort of prediction of the improvement in the CPT result, for instance. So that's the sort of things that have been done. However, there's still a better need for understanding of the soil type, and also we need better numerical tools, because really we can't capture the surface effects. Okay, so this is a big problem in any numerical analysis. At the surface, where the stress is low and the soil gets pushed around, that's really challenging for any numerical analysis. And then there's also the soil dynamics, which is always challenging to capture that, and particularly when the soil is unsaturated, as it often is during the compaction operations. Okay, so that's the end of my presentation. So I don't know if you want me to stop sharing or you want to ask questions about this.
Yes, sir, you can just stop sharing, then we can begin with the question session.
Okay, stop.
Yes, sir, we have one question from Kritiman. He is asking, how do we ensure that the vibratory roller does not oscillate at the resonant frequency of the soil? Or how do we determine the resonant frequency of the soil?
Okay, look, I don't know, about Indian practice, okay? But the way the rollers work at the moment is that they have basically two settings. This is the standard roller. And it either has a small eccentricity or it has a large eccentricity. So that there's basically two settings, fast and slow. And those, when you use those settings, there isn't an issue with it going out of control. So the out of control comes because what's happening is that people are trying to be clever and to then use computer control, ideally, right? So you'd like to optimize your compaction, reduce the number of passes by adjusting the amount of energy that goes in depending on how the ground behaves. And this is when this sort of problem arises. So it's kind of theoretical at the moment, because my understanding is that, and I'm just going on hearsay, but my understanding is that all the companies that have tried to achieve this have failed, in that the machines become uncontrollable when they try to use some sort of algorithm to control them. So I'm sure we'll get better at it, but at the moment, yeah, it doesn't work. That's my understanding.
Thank you, sir. We have another question. How rolling dynamic compaction advantage over normal dynamic compaction?
Oh, okay. Well, yeah, it's really not, it's for a different purpose. To give you an idea, right, there was a site I'm aware of in Australia where they used dynamic compaction over a part of the site where they had deep soil, and then another part of the site where the soil was less deep, they used the rolling dynamic compaction. So I think it just depends on what you're trying to achieve.
Thank you very much, Professor Airey, for sharing your knowledge. Hoping everyone had an amazing learning experience.
Okay, no, it's my pleasure. It's been a fun topic for me, so I hope hopefully you enjoyed it. Yeah.
Yes, sir, we enjoyed it very much.
Thank you, sir. I have one question. In contrary to the normal roller, so we have another factor that is kind of pitch, means the distance between each impact of this rolling dynamic roller. So, what is the procedure? Means what is the criteria that will guide that what will be the suitable this distance? Whether it will be a triangular one, what will be the diameter of the roller? All this.
Yeah. So okay. So the way that is done is basically they try to work out the energy that the different rollers impart to the soil. So if you go to the Landpack website, you'll see. So they have some pretty picture where the triangular one, because the center of gravity rises up more than the other ones, gives you the most energy. And then when you go to the 5-sided, you get the potential energy is much less. So the impacts are smaller. So then it's, you know, you choose the device depending on how deep you want to compact, basically.
Thank you, sir.
That's good.
Thank you, sir. It was so nice presentation that we learned so many things, and that where I have left Sydney. So after that, so many things you have developed, sir. Is really appreciating, and your devotion to this study is tremendous. So many things to be learned from you, sir, and some new techniques that we have heard, and also we have seen how deeply you carry out the research, how the particles move, so many things, and very much interesting, sir, I should say.
Yeah, okay. No, thank you.
And I hope that all our students who participated, they also have learned how a research is to be done, even if it is a small thing, also like laboratory test that you have done, and how deeply we can carry out an experiment that you have shown so nicely. Really, sir, it is appreciating. Thank you, sir, for enlightening us.
Yeah.
Yeah. Sir, we have with us Omit. Omit is also a faculty who is also present. So anything, Omit, you want to say about this webinar or ask something to Professor Airey?
This was a nice presentation, sir. Actually, in this field, though currently I am not working on this field, but it was nice and informative to me. Many practical aspects I learned today. Thank you, sir, for such a nice, informative, and practical-oriented presentation. Thank you, sir. Thank you very much.
Okay, thank you. Good. Glad you enjoyed it. Okay, we done?
Olimpa was there. Olimpa left. Olimpa left. Okay. Okay, then Olimpa. Olimpa, you are there? Olimpa. Okay. Okay, then Swarnali or Devjit, you like to conclude, or?
Swarnali is there? Are you there?
Yes, sir, you can conclude if you want.
So you can conclude now.
Okay, sir. Then with this, we come to the end of our 2 days Terzaghi Day celebration. Hope everyone had an amazing learning experience. So with this, we would like to end our today's session. Thank you very much, sir, for joining with us.
Okay.
Thank you, sir. Thank you. Hope we will meet again, sir. We will again request you to be with us.
Okay. Hopefully I can get to India.
Yes, sir. If you come to India, welcome, sir. My house is open to you, sir.
Thank you.
Please come with family. so that we have very nice scenic beauty in this region of India.
So northeastern part of India is very beautiful. So if you plan it, so it will be a nice tour.
So what time of year do you have to come?
Winter time.
Our winter. Winter of our place means
December,
summer
November,
of your
December.
place.
Right. Yep. Okay. We'll try and work something out.
Yes.
Okay, thank you. Thank you so
Okay.
much, sir.
Thank you, sir.
Also, one thing, everyone is requested to kindly fill the feedback form that is given in the chat box.
Okay, so Sonali, you circulate it in your groups also. So that,
Okay, sir. Okay, sir.
okay, thank you.
Okay, sir. Thank you, sir. Thank you.